Hello and welcome to this ADINA training video. On previous videos, we've shown how to import a geometry, a building structure from another Bentley product. In this case, we're going to use the ADINA Native geometry. And the objective is to show some commands and operations to create a model from scratch that will consist of beam elements and shells. I'm going to show as well how to post-process the model, and I will show how to perform some basic checks to make sure that everything in the model is working as intended. Right, so the ADINA Native commands are under the geometry menu. We have points, lines, and surfaces. We also have volumes, but we're not going to use these ones. And we have also the direct command buttons on the toolbar. We can control the visualization from the View menu, Customize, Commands tab, and Modeling. So if we are missing any of these, we can just drag and drop them to our toolbar. We also see that when we start a new ADINA screen, the line, surfaces, and volumes are grayed out. They are disabled. That is because I can't have a line or a surface if I don't have points first. So a line, for instance, will have at least 2 points. A surface needs to have at least 3 points. So I'm going to start defining my points. I'm going to have points 1 and 2. Point 1 will have 0, 0, 0 coordinates, and point 2 will have 0, 0, 3.8. I'm going to set a isometric view. I'm going to start creating my first column. So I'm going to define a new line, add, click on the B button, select my 2 points, and save. I'm going to add extra lines from the columns that they're going to be copies of the first one. So select the transformation. I will need 3 copies. Double click on the line field, select my line, right click and finish. And I need to specify in which direction and distance the lines will be created. So I need a transformation, add a new transformation, and it's going to be 5 in the X direction. And I'm going to take the opportunity to create additional transformations. I will need another one in the Y direction, and I'm going to need another one vertical in the Z direction. Now I have to pick the right transformation, which is 1. I'm going to create those lines in the X direction, save, and that's our first set of columns. Let's add more lines. We also need 3 copies of, double click on the line field, all the lines, finish, and now my transformation label will be 2. So I have copies in the Y direction. I just need a few more. It's going to be 1 copy again in the Y direction, double click on the line field and pick these 2 front columns. Okay, now that we have the columns, I want to create the slabs for the first floor. So I'm going to show different ways of doing this. So I'm going to add a new line. It's going to be straight. It's going to be between these 2 points and save. And now we go to the define surfaces command, add a new surface by extrusion, double click on the line field, select my line, right click and finish. And I want 5 distance in the X direction. When I click save, that has created the surface. And it's a good way of making sure that things are connected. I'm going to display the surface label. You can see that the normal is in the vertical direction. The little rectangular here shape marks the local X direction or the local R direction of the surfaces, and the third one, well, is in the same plane and orthogonal to local X or R. Right, now we're going to continue doing the same. So add a new line by extrusion, X equals 5, double click on the line field, select the line, right click, finish, save, and repeat the operation with this line, right click, finish, and x equals 5 and save. And we see that all surfaces are oriented in the same way, which is very important. Now we create surfaces in the orthogonal direction. So we save. It's going to be extrusion in Y. Double click on the line fill, select one line, and I could select the other lines manually, but I'm going to right click auto chain, selecting all those lines, finish, save, and equally. Let's actually copy into 7. And instead of having an initial line of 0 here, double click on the line fill, select, right click, auto chain, right click, and finish. We save. And finally, we just need one more surface. Double click on the line field, select that line, right click, finish, and save. And that has completed our the geometry for the first floor. I now need to start creating copies in the vertical direction. So I'm going to start with my columns, define new lines, add, transform. I will need 2 copies. The transformation level this time will be 3. It's the one that we created in the Z direction. See that more transformations have been created while I was extruding, but I don't need those ones. I need my transformation level 3. I'm going to make sure points get connected, select my lines, and now selecting the columns is a bit, perhaps a bit tedious, so I'm going to rotate this a little bit, and when I do my selection, I'm going to select everything but the columns, right click and invert. Right click and finish and save. So now we have copies of the columns, and I'm going to do the same with the surfaces. So define new surfaces, add, it's going to be actually by transformation this time. So we need 2 copies as well, transformation level 3. We're going to checkpoint connectivity and select all my surfaces, right click and finish. And now we have our full building geometry, and we can start defining our engineering properties, mesh, and so on. So I'm going to switch off the label visualization. And the first thing that I'm going to do is define material, elastic isotropic. I'm going to have one single, for instance, concrete material model. And we're going to assign a Young's modulus, Poisson's ratio, and density. Remember that we're not specifying any particular sets of units. We need to make sure that the dimensions, forces, masses, and material properties, and so on that we introduce are all consistent. So we click OK, close. Now I'm going to define my cross-section. So I'm going to add a new cross-section. First one will be for columns. So I'm going to define a square section for the columns with this dimension. Save and add a new one that is going to be for the floor beams, and it's going to be of these dimensions. We click OK, and now we are ready to create our element groups, which we can do through meshing element groups or use the direct command button on the toolbar. We add a new element group. It's going to be a shell for the slabs. Let's call this, let's give it a description. The default material is concrete, that is fine, and our element thickness is 0.2. Save, and I'm going to create my beam elements for the columns and the floor slabs. So I need to go to type and pick a beam element. We call this column material 1, cross-section 1, perfect, save. And let's copy, for instance, this into group 3. And we just need to change the description to floor beams, and we need to change the cross-section to cross-section 2. We click save, and now we have the 3 element groups, and we are almost ready to start meshing. First of all, we're going to define a mesh density for the model. We're going to control it with lines. We're going to have, for instance, 10 number of subdivisions for all lines. Double click on the line field, select the entire model, right click and finish. Save, and that has updated the mesh density. And now we can just start assigning our element groups to the different parts of the structure. So we go to meshing, create mesh, surface. We pick a shell element group, double click on the surface field, and we can just select all surfaces, right click, finish, and OK. And that has meshed our slabs, our floors. Then we go to create mesh and lines. We start meshing, for instance, the columns. So we want element group 2, as we defined it in here. Again, we're going to switch off the mesh to select those columns, double click on the line field, select everything except of the columns, and then right click, invert. So we have all the column lines selected, right click and finish. Now, the cross sections assigned to the columns, they are square. So the orientation, whether it's the vector is 1, 0, 0, 0, 1, 0, is not particularly important. I'm going to explain this next. So this is going to mesh our columns as well. And now when we mesh our floor beams through meshing, create mesh, and line, now the orientation is important because those cross sections are rectangular. So if we go to the help here on the mesh lines dialog, select on beams, and we see we're being told that the element S direction lies in the plane defined by nodes 1 and 2, which are the two nodes of my beam element, and either the auxiliary node K or the orientation vector. So we're controlling the orientation through the vector, and we see that the S aligns with this orientation vector. So if we go to the section, we see that S corresponds with the width that we want to be parallel to the horizontal plane. So we want S to align with the horizontal plane. In this case, it's Y. So double click, well, we're going to pick a 0, 1, 0 vector, double click on the line field, and for these particular lines, we need a vector of 0, 1, 0. So I'm going to select my lines. And then when we choose the orthogonal floor beams, we will need to change the vector. So right click, finish. Another thing before I click OK, we need to make sure that these beams will be connected to the shells, the floor slabs that we previously defined and created. So from nodal options, let's do a nodal coincidence check for all the generated nodes, not just the ones at the boundaries. So we click apply, and that has meshed some of our floor beams, and we need to repeat the operation for the orthogonal ones. Now we have to change the vector to 1, 0, 0. Double click on the line field, and we just select the remaining beams, and that will complete the entire mesh for this building structure. Right click and finish. We check that we still have this option selected, all generated nodes connectivity. Click OK, and now the full mesh has been applied. So we can clear the screen and visualize a new plot. One useful verification at this point might be to make sure that everything has been defined and applied as intended. So we can go to Modify Mesh Plot, go to the element depiction, display beam cross-section and the shells by the full thickness representation. So click OK, turn off the geometry, and I'm going to make this shading solid. And now if we zoom in, we can have a closer view. So we see the thickness is reasonable, and we see that the orientation of the beams is correct everywhere. We could also display a band plot by thickness. Let's bring this back to the original view, apply, and we see that we have a 0.2 thickness everywhere. Or I could, for instance, display coordinates. Give me the Z coordinate, for instance, and we can see that they go from 0 to 10.40, to 11.40 actually, sorry. So that is actually the 3.8 times 3. So everything seems to be correct at this point. So let's again clear and display a new mesh plot. Right, so now we have a full correct geometry and mesh, and now the only things missing are supports and loading. So let's start by defining some fixities, some supports. We have by default a fully fixed boundary condition. Double click on the point field, select all the points at the base, right click and finish. So we display supports, we see that these have now been applied. And in terms of the loading, I'm going to have a overall self-weight of the structure, and then different pressures applied at different floors. So I'm going to have 4 independent load cases in total. So to control that, we go to Control. I'm going to do this through time function. I could also switch to load cases, but I'm going to use time functions this time. So we have 4 load cases in total. So I need 4 time steps, and I'm going to control the value for one time function. So this will be, for instance, for self-weight, and it will have a value of 1 at time 1, but it will be 0 at the rest. So we can analyze each load case independently. Save this time function, copy, and now we want the value to be 1 at the second time step. Copy, the third time step, save and copy, and the fourth time step. And save and OK. Also, we need to make sure that all those 4 time steps will be solved. So from control time step, I'm going to select 4 time steps and OK. And now we are just ready to start creating and applying the loads. So from the apply load command button, which again, I can access through, for instance, the model menu and loading, I'm going to use command button. First of all, a mass proportional loads, define, add a new one. In the Z direction, I'm going to apply the acceleration of gravity. OK, time function 1, and applies to the whole model. Click apply, and now we start creating our pressures. So the first one will be, all of them will be surfaces. I need to start defining them. Add a new pressure. It's going to be 5,000. Let's call this floor 1. Having different pressures at different floors will help a little bit with the definition. So I'm going to have copies for floor 2, save and copy, and floor 3. Save and OK. Switch off the mesh again. So we're going to start with the floor 1, double click on the surface field, pick all the surfaces, right click and finish, apply. And we see that by default, these fields have been populated, and we need to change the time function here to 2. So I could do this manually here, but thankfully we can copy and paste this into a spreadsheet and bring it back in the same way. So I'm going to open my spreadsheet, paste those rows, going to change the time function to 2, and I can bring this back to the ADINA interface in a rather seamless manner. And then for pressure 2, again, double click on the surface field, select my surfaces, right click and finish, apply, and then copy the entire all the rows, and time function should be 3 this time. Copy and bring this back in. Apply. I could just bring the columns. That will be a possibility as well. So double click on the surface, finish, apply, and then we could just bring this column if we wanted to. Actually, we could. There is different ways we can do this. Copy and bring it back here, and that's it. Apply and OK. So let's clear and plot a new mesh. And hopefully, if we have now applied our loads correctly, we can plot the load. We see that that's time step 4, that's the top floor load case, the third the second one, and the overall gravity. Actually, we can see that the described pressure here is bigger than the other two, so I may have made a mistake. Let's go back to the control time function. In the number 4, we see that it has multiplied my 5,000 by 4. So this should be 1. It was a mistake that I introduced. Click OK. And now we see that all the floors, they have the same and arrow size, and it has been applied correctly. So we have now verified the geometry, the mesh, the loads and supports, everything is correctly applied. Let's just move on to solve the analysis through the data file solution command button. Save. It's going to run 4 time steps, and that has now completed the analysis. Let's switch to the post-processing interface, and we can open and visualize the results. So I'm going to focus on some basic checks that we can perform at post-processing to make sure that the structure is working well, we define everything properly. So the first thing, really quickly, we are displaying right now the deformed shape, but obviously under normal loading, a building structure should have really small displacements, so we can see them very well. So I'm going to scale the displacements. This does it automatically, but is slightly too large. So we can go back to the modify mesh plot, model depiction, and this, well, let's display this to, for instance, let's say a factor of 800. Click OK, and that looks, more reasonable, allows us to see the deformed shape. We see that it's symmetric. We see that there is no mesh discontinuities or cracks. No supports are missing. So the general shape looks good. The second thing I always recommend is to look at the magnitude of your displacements. So if we look at the Z displacements, for instance, under self-weight, we have something in the range of just under 2 millimeters, which is reasonable. If we had, for instance, made a mistake with some of the units, or the Young's modulus was out by a factor of 1,000, or for instance, a cross-section or the pressure that we have applied, then this would be, we could see that there is clearly this a few orders of magnitude out or wrong. So we can go through different load cases. So we have 1 millimeter, 1.2 millimeters, and 1.4 millimeters. It makes sense that the highest, we have more displacement, but all looks fairly sensible and symmetric. The next thing is to look at internal forces on beams and shells, at least qualitatively. So let's clear the bump plot, and let's look, for instance, let's go back to the first, the self-weight time step, and let's look at stresses on the shells. So we go to the stress. I'm going to look, for instance, at global X, which is one of the main directions of this building, one of the principal directions. Stress is OK. I'm going to smooth them out. And we see that we have areas of tension and compression, which is what we expect when we have bending. So by default, we're looking at the top fiber, at the top surface of the shell. So we can see that we have compression at the sagging zones, and we have tension at the hogging right on top of the columns. If we modify the bump plot and we come here to result control, and we pick, well, actually, I want the bottom shell results. Click OK and apply, and we see that this has now been updated. So at the bottom of the shell, the areas of sagging, they are in tension, and the hogging areas, they are in compression. This is why it's really important that we have the surfaces consistently oriented, which is what we achieved at the beginning. We check the labels of the surfaces and so on to have consistent sets of stresses. We can also, let's switch the stresses off, and we can put the undeformed mesh. We can also look at, for instance, axial force bending moment diagrams at the columns. So let's do this through display, element line plot, let's create, for instance, an actual force. And then on the plot style, let's select group 2 that corresponds to the columns, OK, and OK. So we see the columns, obviously the ones in the middle, are subject to more compression, and we see that the compression increases as we go down to the floors because of the accumulation of weight of the structure. And we could look at the different stories. So this is story number 1. So for instance, in this case, we only have the bottom column under compression. One last basic verification might be to look at the sum of the reactions. So we want to make sure that the loading has been applied as intended. So we could take, for instance, our pressures at the floors, and we know that we have a distance of 5 by 5. So let's go to a spreadsheet again. So we have an area of 5 by 5, and we have a pressure of 5,000 that we applied, and we have 10 surfaces in total per story. So if we do the product of these three, and we put this in scientific format, we have 1.25 E6. So let's go to list, value list, and so on. And for the whole model, let's look at the total reaction in the Z direction, the reaction done. We click apply. Yeah, and we can see that for floors, so for load cases 2, 3, and 4, which is the loading of each independent story, we have exactly 1.25 E6. So those are the basic verifications that we can and we should perform to make sure that we have applied everything in the structure as intended, whether we want to use this for design directly or whether this is the starting point for a more complex analysis, as we're going to show on our next video. This is all. Thank you very much for watching.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.